Hey guys, welcome to a simple pendulum. And for those of you who are not in class today, when you come back, we'll do a quick demo about what that actually is. It's pretty straightforward. A pendulum is a mass at the end of a lightweight cord. And once again, we assume that the cord does not stretch and its mass is negligible, so a massless string. We call the thing at the end a bob. B-O-B, so that could be a washer or any other object. But that's what a pendulum, it swings back and forth. We all kind of know what that means. So this slide looks super mathy, but it's just a quick version of how we end up getting there. So we have forces at angles, and we have some components that we kind of know about. But ultimately, what happens is the most important piece is this less than 15 degrees or so. That's what makes pendulums work. If they go past 15 degrees, it swings too far. The string doesn't quite do what it's supposed to do. And so once again, we'll have a quick demo about that. But there's lots of forces, or there's a couple of forces going on that we sort of need to know about. But once again, it really just swings back and forth. So we don't need to know all of that math here. Again, we understand that a spring oscillates back and forth, like we've learned, and a pendulum oscillates back and forth. So we have this interesting idea that the period of the spring was 2 pi square root of m over k. So it had to depend on the mass attached to the spring and the spring constant. Well, if we have what we can approximate for k up there, that mgl, when we substitute for k, we have these equations down here that we will be utilizing for a simple pendulum. The period of the pendulum, 2 pi square root of L over G, and frequency is 1 over 2 pi square root of G over L. And so notice they're just backwards of each other. They're inverses of each other. Notice the m canceled out. The mass does not matter how fast it swings. It could be a 1 gram weight or a car. It swings back and forth. And once again, we'll do a couple of demos that illustrate that. It's really interesting how that works. Really just depends on the length of the pendulum and gravity. And so we can kind of see the relationship there. So a couple of quick examples here. The period of a simple pendulum. So here's my given information. A length of 2, gravity is 9.8. So we'll obviously use the period equation, substitute stuff in, and here we should get 2.8 seconds. So that is how long it takes to swing from the original position all the way forward and all the way back. That is that one complete cycle for 2.8 seconds. So the frequency, basically we could have solved the other one and just flipped it, but here we're given what is the frequency. The frequency equation is just 1 over everything. Everything is just flipped. And then we get 0.3 hertz. And so once again, that is how many complete cycles in 1 second. And so this only gets a third of the way through its motion in 1 second. So it could be kind of a slow one. So that's the back and forth motion, frequency and period. And then we have to talk about the energy in the pendulum. So we have 2 types of energies. We have gravitational potential, and that makes sense. It's at its apex, at its highest point on either side. We have gravitational potential energy. And then we also have the kinetic energy of the mass, 1/2 mv squared. So instead of elastic potential like we worked before, it's just going to be gravitational potential and kinetic. And we understand that the total mechanical energy is constant in this case. So here we have E total. So we have the gravitational potential plus kinetic. There's everything written out. So once again, mechanical energy, it's just we're using actual things. So that's why we call it total mechanical. So it all has to be the same at either apex, right? It's going to either be all kinetic or all gravitational potential. At the bottom of the swing, so we'll have some diagrams that should go along with this, but at the bottom of the swing, it's its fastest. And then at the apex, or the amplitude, the biggest amplitude on each side, it's going to be at its slowest. So just like a spring, just like the springs that we were working with. So a quick example on how this works. So the energy of a simple pendulum, we have the mass, we have the gravity, we have how high it's going in reference to itself. Then we have how long it is. So the gravitational potential energy is a maximum when the pendulum reaches its maximum height. Well, that makes sense. And so the gravitational potential energy is equal to mgh. And so that is how many joules of energy it has. So when we do this, we can look at the same kind of question when we're looking at maximum kinetic energy. If we know, so it looks like it's the same information. We know that total mechanical energy is conserved. The maximum kinetic energy is equal to the maximum gravitational potential energy. So we're just stealing that number. And so we know that there is a maximum energy at the bottom, which is the same as the top. And that's that 0.39 joules. That was that value from before. So let's see how fast one of these is moving. So same question, same given information, and we just now want to figure out how fast it's going. Well, we're going to use the kinetic energy equation to solve for the maximum speed, that 1/2 mv squared. So we're going to solve for V max. And here's my given information. We solved for V, and then that 0.39, we stole that from the previous slide. So same question. So this is basically part A, B, C of questions that you'll encounter. So that's pretty much it. We have some basic ideas that are extremely similar to the springs we've been working with, only in this case we just have the length of the pendulum. And then the gravity associated with, that's what makes it swing back and forth, whereas that spring we were working with before was based on mass and the spring constant. All right, that's it for now, pretty short, and let me know if you have any questions. I'll talk to you later. Bye.